We've done this in a while, so welcome everyone. Thank you, and I would like to thank the organizers for this wonderful workshop and the kind invitation to speak here. So as you can see today, I'm going to talk something about quantum error correction codes and holography. So it's been 7 years since Amahara and Harlow first identified this wonderful story between holography and ADSC, holography and quantum error correction. But quantum error correction code has been developed for something of a different reason, right? Because we use it mostly engineered to solve a problem in quantum computing where we want to keep our quantum information intact. Then occasionally errors do happen to our quantum information, so we would like to correct those errors and to undo the effect of these errors. But more often than not, we're not able to do that perfectly. Right. So those codes in which we cannot undo the errors perfectly, but you can undo them approximately, we call them approximate quantum error correction codes. Now, from a quantum computing point of view, it seems less than ideal, right? Because we want to be able to just get rid of these errors entirely. However, in this talk, I would like to emphasize the following point, namely that what looks like imperfections and impurities from a quantum computing point of view actually help our cause here in quantum gravity. And in fact, I want to mention the central point of the paper is that these impurities or these imperfections in quantum codes are not something we tolerate or something we want to get rid of, but rather they have profound physical consequences in ADS-CFT and hopefully also beyond. So let me first talk about what's a quantum code, right? So here by quantum code, I just mean the most general sense. It's a collection of code words, typically designated as a space, a Hilbert subspace. So this is called the code subspace, which is a subspace of this, that's often referred to as the physical Hilbert space. So the scenario we're imagining is that you have a lab, you have a bunch of qubits that you can control, right? And each qubit sort of corresponds to a tensor factor over here. And then you can encode your important message that you would like to protect against quantum errors in this code subspace C. Now, there is an easier way to track what this code subspace is, namely through an encoding map. So this map is a linear map that maps you from this logical subspace, which is the input space. This is the space of information that you want to encode or you care about. And you want to map the information in this space to the physical Hilbert space, which is the space of your physical qubits. So, well, this talk I'm going to take on this very code-centric perspective, but every now and then I'll also refer back to ADS-CFT to help us gain some intuition as to what the code is doing, right? So we will use some graphics and intuition from ADS-CFT to understand what exactly the code is doing. And just to give you, so we just talked about codes in the very general sense. So we know that ADS-CFT can be thought of as a code, right? Where I just define my code subspace as the low energy subspace of the theory. So then you can identify these degrees of freedom, right? So what tends to happen is that the logical degrees of freedom, which are the things that you want to be protected against errors, those are identified with the bulk EFT degrees of freedom. And the physical degrees of freedom, the things that you presumably control in the lab, is they're identified with boundary degrees of freedom, right? So obviously that defines a code, but what's so special about this code? Because from last slide, it just seems like I choose a subspace, but what's so special about the subspace? Well, obviously, we want to choose a subspace that has code words or has states in that subspace that are robust against certain kind of errors, right? So choosing the right subspace is actually non-trivial. So here we would like to choose the subspace or a code that can protect the information from so-called erasure errors. So here's a very simple example of 4-qubit code, which we will use throughout the talk. So in this example, we'll encode the 0 state into this GHZ state and call it 0 tilde, and then we'll encode the 1 state into some similarly GHZ-like state and call it 1 tilde. And together with these states, you can define a code subspace, and that defines you for what the quantum code is. And graphically, I'll also use these notations. This is a tensor that represents the encoding map V, which encodes this one logical degree of freedom colored in red as input, and then encode that into 4 physical degrees of freedom, which are the in-plane legs. And similarly, this is the same tensor. You look at it from top down, where the logical degree of freedom is denoted by this dot over here. So this code is an erasure correction code in the following sense, that if I have some information that I encoded, call it psi tilde, which is a superposition of psi 0 tilde and 1 tilde, and then you lost qubit number 4. But all is not lost, right? So you can still recover the information that you care about in this psi 1, as long as you can just have some unitary accent, the qubits 1, 2, and 3. Okay, so in this sense that we can recover this information, and it's protected against erasure errors. So a familiar analogy with holography that everyone has seen so far, perhaps with the Qtra code, but now with the 4-qubit code is the following, right? So we can make an analogy where the right-hand side is basically a spatial slice, right, in ADS-CFT, and then I can divide the boundary region into 4 equal intervals. And then if each interval is analogous to a qubit on the left-hand side. And also, I mentioned before, right, I'm identifying some bulk degree of freedom with the logical degree of freedom in the code. Now, you have some analogous erasure correction property is that if you have a bulk operator that's acting in the center of ADS, we all know that it can be reconstructed on the subregion 1, 2, and 3. Through entanglement wedge reconstruction. So analogously just means this, right? But this is equivalent to the fact that if you have control over intervals 1, 2, and 3, you can reconstruct the information that's encoded here, which is precisely what we're seeing in the code. So these are analogous to each other, right? If you raise one of the intervals or one of the qubits, you can still recover the information that's inside. But that's not the only, so this imagery is not the only connection though. Dan Harlow realized this, that there's also a notion of RT formula that you can define in the quantum error code. So again, I'm not gonna go through all the details, but the rough intuition is that when you have a quantum erasure correction code, you're guaranteed a recovery procedure that undoes does the effects of erasures. So for example, here again, the 4-qubit code, but let's say you erase qubit number 4. Nevertheless, there's a mapping that allows you to undo the effect of erasure. And then in effect, you are recovering the information I care about inside, and you have a leftover piece. So whenever you have the erasure correction code, you can always do this. And the consequence is that you can divide the information in the state into 2 pieces. The first piece is the information of interest, and the second piece is this leftover piece. And this piece turns out to be also important in building non-trivial quantum codes. And more generally, this of course applies beyond just the 4-qubit code. It can look like this, or if your code is algebraic operator algebra error correction, then it can look like that. But the point is, there are these 2 pieces, right? By having erasure correction, you have these 2 pieces, and you can then compute the entropy on both sides of the equation, right? So that would have turned this formula into an entropic relation, where the left-hand side is simply the limit entropy of some physical subsystem, and the right-hand side actually divides into 2 pieces. First is the entropy of the encoded information, and the second is the entropy of this leftover piece. But there's a natural correspondence with ADS-CFT, especially when the code is built on the tensor network. So your code also looks like it has some geometry. We can identify the first piece, the encoded piece, with the bulk entropy contribution in the RT formula, FLM formula. And the second piece, the entropy contribution, I can identify with the area term. So by suitably defining an area operator, which depends on the entanglement entropy. Okay, so that's what we have for all these erasure correction codes. Nevertheless, it's not quite enough. So what we see so far is that so it turns out those RTPs that you can check for the 4-qubit code or for any exact erasure correction code that we know about so far is that they're always constant. In other words, the area operator that we saw earlier here is trivial, which is proportional to identity. What does that mean, though? So if we just put on our ADS-CFT hat for a little bit, suppose our bulk state is initialized in some vacuum state. And of course, from this bulk stress energy, we can use Einstein's equation, we can figure out what background is, and then from that background, we can figure out what the normal surface areas are. Right? So that gives you a set of data. However, if you now add some stuff into the bulk, and the bulk matter distribution have changed, that in principle, and based on that, it would generate a different background geometry because through gravity, different bulk stress energies giving you different backgrounds. And from different backgrounds, generically should be expecting a different minimal area data. However, here, nothing of that sort is happening. No matter what kind of bulk state you're putting in, aka the logical state you're putting in, the resulting area term is constant. So this is more like QFT on, this is more of an analogy of QFT on fixed background. So how do we put the gravity, or how do we put this non-trivial area operator back? One of the answers is to make the code worse. There's actually a number of reasons why we expect this to work from an error correction code point of view, but I don't have the time to go into this. Rather, let's just look at just make the code worse and see what will happen. More often than not, right, when we're, say, preparing a code in the lab or doing actual quantum computing, there is noise and nothing is perfect. So when you are, let's say you want to prepare an encoding map, or you want to prepare an error correction code that's characterized by this V0, which is encoding isometry, very often you don't really get to V0 exactly, but you pick up some noise terms, right? And where each VI is an encoding map of a different error correction code. Now, the epsilon overall, it defines an encoding map of a noisy error correction code that maps from, takes you from like input logical space to output physical Hilbert space. Well, this is more realistic in the sense that when you have experiments and you have noise, that's what happens. But it's also what we sort of expect from ADS-CFT anyway, once you just include the 1/n corrections. So let me give you an example. So here's an example of an approximate quantum error correction code. So what we're doing is all the difference from the 4-qubit code that we've seen so far is that we're adding alpha and beta into the definition of this one state. And this encoding map is will represent it as this brown square from now on. Now, so when alpha is equal to beta, we get an exact error correction code, exact erasure correction code from before. However, when alpha is not equal to beta, or alpha approximately equal to beta, this is an approximate error correction code. Meaning that if I erase, say, one of the qubits, now no matter how hard I try with the other 3 qubits, I can only reconstruct the encoded message up to a small error. You can also see this more quantitatively in the following way, that, right, so I can, for example, entangle my cowords with a reference system, and the reference system is supposed to keep track of where the encoded information or where the information that I care about is being distributed in this code. And so if you do that, and then you compute, say, the mutual information between the reference system and one of the qubits that you erased, you'll find that this information is greater than 0, right? So what it's doing is that now there's a bit of information about the encoded the logical state that's being leaked into qubit number 4. So once you lose it, now there's no way you can cover everything perfectly. There's a similar, there's an equivalent way to see this kind of approximate erasure correction from the operator point, reconstruction point of view. So when you had perfect erasure correction, then your logical operators, like logical X and logical Z's, can always be reconstructed on a subregion, on the boundary, quote unquote. However, now if you have a approximate erasure correction code, then that's no longer possible for the logical X operator, and that's has support now over all 4 qubits. So in principle, you can never reconstruct the X operator with perfect fidelity on the subregion on the boundary. And there are some immediate consequences of this noise injection. So I'll go through them one by one, and then in the meantime, I'll draw analogy with holography by giving you pictures. So the first one doesn't have a picture. It's just the idea that if you work through the details of this code, you'll find that the area operator is non-trivial, which means that now the area contribution, remember that we split the entropy into 2 parts. Now the area contribution in the second part can depend on the logical state of that you put into the code, which analogously speaking means that if you put in a different EFT state in ADS-CFT, now it can lead to a potentially different background geometry that has a different area contribution. The second one has pictures. So there's also a degree of state dependence once you introduce these noise into the system. So for instance, if your logical state is being fixed in the 0 or the 1 state, like the one over here, which I'm going to denote using this yellow square, you can try to do reconstruction. So for example, you lose a qubit number 4, and then you want to reconstruct or recover the encoding information from qubit 1, 2, and 3. It turns out we can do that exactly. So this is always possible when the state is fixed in these 2, and then now you sort of have analogous picture to recovery in holography when you have a pure state in the book, and the recovery is exactly complementary. However, when you change your state to something else, that's not a 0 or 1 state, let's say the superposition of these 2 states, then you find that there is no way to reconstruct the encoder state with perfect fidelity from just qubits 1, 2, and 3. So this is somewhat analogous to the second picture, where you have a no man's land in the center of the. Now, how do we make sense of this? Well, the reason in quantum error correction code is quite clear. Namely, this is because the X code subalgebra and the Z code subalgebra, they all have different support over the boundary region.
Can I ask a quick question on the previous slide?
Yep.
I didn't understand why the entanglement wedge jumped, given that this is still a pure state.
Yeah, very good. So this is a good question. So this is still different from holography in that sense, but this is because the code that we're using is somewhat pathological. It only encodes 1 qubit. So whenever you have a subregion, it turns out that if you reduce the bulk state into that subalgebra, it will look mixed, even though the state itself is pure.
Shouldn't we worry that that means that this doesn't capture the way that the area is non-trivial in holography? I mean, it somehow makes the term that looks like the area more interesting, but maybe not more interesting in the right way.
Good question. So yeah, so actually, I think this is purely because of the code subspace is too small. If you go to random tensor networks, a similar kind of thing will happen. But when you have more qubits, you see things that are less pathological.
What I'm worried about is that this should never happen.
Can I also make a comment? So about the area operators. So in this model where the alpha is not equal to beta, right? So if you take alpha equals to beta, then the area operator is a C number. Mm-hmm. And so then if it's not, so then when alpha is not equal to beta, then it seems, I don't really see how to define the area operator in an approximate setting, right? It seems like the dependence of the operator on the state may just be of order the errors, the approximateness of the code. So it doesn't seem like there's a very sharp statement there.
Yeah, a good question. Yeah, so so there are 2 ways we're circumventing this in our paper. The first is that we do a state-dependent definition of the, so in the example that I showed you here, this actually doesn't matter whether it's alpha is not equal to beta or not. It turns out that when you consider, say, a 2 by 2 definition, you can always just find this because the Z sub algebra is still exactly accessible on both sides. So you can still define an area operator like this.
But I mean, I could also define the area operator to just be S of chi naught times the identity, right? And then that would be true. The formula would be true to within the noise, right?
It would be true within the noise, yeah. But if you include, if you want everything to be exact, then
well, if everything's exact, then it's a proportional to the identity, right?
No. By exact, I mean you treat this code exactly as it is. You don't just ignore the noise or the epsilon as something that you want to get rid of or you tolerate. Instead, you define this code as is.
Well, I guess that's different from holography also, right? Because in holography, we would say that the quantum extreme on surface formula is true up to order effects that are e to the minus s, which we don't try to capture using the bulk picture, right?
Sure, but here I'm not trying to do ADS CFT. I'm just trying to, find some analogies. But definitely, I think those are very good points. We should definitely discuss this afterwards.
Okay.
Yes.
Like I don't think this community appreciates how radical the state dependence is. Because if you put in a mixture of two states or a mixture of two, or I do it like one of two unitaries, you just have no idea what the decoding, how to decode it on the boundary. And you can use this to superluminally signal. It's really pathological. It just feels like, and I guess it also feels like that I kind of lose sight of the duality because I no longer, I lose the predictive power because I can do something different depending on what state is in that block.
I think I agree with those things.
You could just say it's a violation of quantum mechanics, right?
That's right. And you were trying to say that.
Well, here there's nothing violent because the encoding is completely unitary. The encoding is isometry.
But there is a violation on if I now feed in one of two states. If I flip a coin and feed in a mixture of a few states, or if I'm trying to decode an operator and I do one of two operations or one of two unitaries, then what happens in the encoding is not the unitary.
Mm-hmm.
You say the recovery map is nonlinear, right? So it's not a quantum channel.
No, but
I think these are really great points, but maybe we should discuss them in the question answer period. Should let Charles
Appreciate all the questions. I think these are wonderful points that we should try to clarify. Where was I? Okay, so here, the reason we're seeing this, I would like to just mention briefly, is that the intuition is that different portion of the code subspace is not equally accessible to you. So the part that's like logical 0 and logical 1, those are accessible on the subregion, whereas if you are in some other parts of the code subspace, that's not accessible on the subregion. And this is a similar underlying mechanism that gave you the kind of behavior in random tensor network. The third point I would like to make is this analogy with graph operators. I'm not going to define gauge root or anything like that. So it's mostly just it's mostly a superficial analogy, but we will see there seems to be something interesting going on here. So recall that each of these noisy quantum codes can be decomposed in the superposition of these otherwise exact erasure correction codes. And here, let me call the first term the reference code. This is the code that has the most amount of overlap with the code on the left here. And then you also pick up some noise terms, and each of these noise terms is defined by an encoding isometry. Okay, but similarly, I can also think about decomposing the logical operator in the same way. I can decompose my logical operator, logical x, which is logical operator of this code, into the logical operator of this reference code and plus noise, which is very small, hopefully. The analogy I like to make is that this reference code logical operator is somewhat similar to their operator, whereas the skewing or the correction is somewhat similar to the regressing. So, so going back to this comparison table, right? So there's Oh, now I'm running out of time. So essentially on the left-hand side,
You're fine, Charles, you're fine.
oh, fine. Okay. So on the left-hand side, the code that we would like to, so this is a code that's noisy, but at the same time, I would like to argue that it's analogous to some EFT coupled to some effects of gravity. So in ADS EFT, if you take and G goes to 0, you get some decoupled limit where the matter field does not back react on the background at all. And that corresponds to the reference code, because earlier on we saw this area operator doesn't work. It's trivial. So if you take the reference code logical operator, it works fine in this reference code limit, or it works fine in this QFT on fixed background limit. But as soon as you turn on gravity, this guy is no longer the correct logical operator you should be considering. In particular, it doesn't take states in a logical subspace to another state in a logical subspace. So in this sense, it doesn't look like a physical operator, but you can make it physical by adding this noise term. But the cost you pay is that you will have to smear information all around the place. So now, instead of having an operator that's only supported on the subregion, you have an operator that's supported on these different qubits, and the information would have leaked into some complementary region because of this term. So it is in this sense as similar to dressing, because if you think about like scalar field on curved background, and then you couple it to gravitons, the dressing will render the operator non-local, and it will smear the information and leak some amount of information to the complementary region, thus rendering a approximate quantum error correction code. Here's the summary so far. We saw these consequences by going to the noisy regime. There's one more point I would like to make, which noise does, but I will require more logical qubits. So here, let me construct a more sophisticated model using tensor networks. So here, this tensor network is built out of these 4 qubit codes, or each of these brown squares is a noisy code that we just saw before, and each of these hexagons is a perfect tensor. So since we won't be talking about the specific properties of these codes right here, I won't go into the details of what exactly is a perfect tensor. But the point is, this tensor network defines a noisy encoding map from these logical degrees of freedom, represented by these red dots, to the physical degrees of freedom that's on the boundary. Okay. And now, if you take the noise term, the epsilon to 0, it will recover something that's an exact erasure correction code that's very similar to the happy code. In that, you can define the same thing like entanglement wedges. You can do boundary reconstructions of bulk operators. Everything works just fine the same way as the happy code in this limit. And the point with these code in the 0 noise limits is that each of these red dots are independent degrees of freedom. They actually represent tensor product qubits that you can manipulate independently on the boundary. So you can change the state here without affecting a state somewhere else. However, now if you turn these noise on, first of all, the tensor network inherits all these other properties that we discussed earlier, but just making them a bit more complicated. Here are some pictures that I can show here for the analogous entanglement wedge story. But an important point here that was absent in the previous model is that the bulk qubits that appear independent here actually aren't independent. So what I mean is the following: if I treat the boundary Hilbert space as the physical Hilbert space, and everything going on here is the one that you should be paying attention to, whereas the bulk is an effective description of the physics that's going on the boundary, then what you will find is that if you act a particular operator on the boundary and you wanted to change the logical state over here, it turns out inevitably that you will have also modified the state a little bit over here. So what is happening? The answer is that, the quick answer is that the bulk qubits are actually slightly overlapping, in that this picture that I'm showing you is a lie to children. It's sort of deceiving. Let me make it a bit more precise in the following way. It turns out that these encoding maps that we constructed using this tensor network is non-isometric. So this can be seen from the previous definition. So if you recall that V naught are encoding isometries, then we recognize the superposition of isometries is not necessarily isometric. So this encoding map is generally non-isometric. And if you're familiar with the tensor networks, it would turn out that each of these Brown squares or tensors are actually non-isometric. So by contracting a bunch of them, I'll obviously also make you a non-isometric encoding map. So the consequence, of course, from this tensor network is that we're mapping orthogonal states to states that are almost orthogonal. So if you take I and J, which are orthogonal, you do mapping to the I tilde J tilde, the encoded version of the I and J in this tensor network, you'll find that they're not really orthogonal, but up to this slight overlap here. Equivalently, that means if you were to insert, say, a logical operator somewhere here, and then another logical operator somewhere down here, and compute the commutator, you will find that the commutator is actually not zero, but it has a small contribution for, depending on epsilon, which goes to zero in the limit epsilon goes to zero. Now, this is also similar, or reminiscent of the things that we see in gravity, in that if you have a scalar field, say, or some matter field on the background that's not coupled to gravity, then everything, you expect everything to commute in this QFT local QFT kind of understanding. However, as soon as you couple these things to graviton, then you need to add addressing to these operators to make them gauge invariant. And in doing so, you have made them also non-local, and then you can compute their commutators, and their commutators actually aren't generically vanishing because of the dressing. So a similar thing is happening here in that the bulk qubits are the picture I'm drawing for you is, thank you, deceptive. In the sense that if you actually think of a physical process that's doing the encoding, it's mapping, this physical process should be taking you from some non-factorizable Hilbert space into another Hilbert space. But here, because we insisted somehow we humans like to think about things in terms of local terms, the price we pay for locality is introducing these small overlapping contributions. So, but overall, at the end, you're not really having a factorizable Hilbert space in the code substrate. So to summarize, by going to these by going from exact erasure correction codes to approximate erasure correction codes, we're seeing a number of these consequences that are similar to what we expect in gravity, and we only recover the sort of naive limit when we take the noise to zero. So a little bit of discussion. So this noise also has other kind of consequences. For example, it will construct for you non-trivial two-point function. And at the same time, we're sort of seeing a vague analogy between the noise parameter epsilon and the gravitational constant. It seems like there might be something going on there. So as part of future work, I think it would be worthwhile to understand all of this in random tensor networks, for example, because this is all built for this one specific model. The random tensor network itself is an approximate error correction code, and all of these things can be made more precise in general. There also seems to be interesting experimental connections, because here we're taking advantage of what the noise is giving us. So in usual quantum computing, we want to get rid of noise as much as possible, but here it seems like noise is a feature, not a bug. So maybe we can use the noise to learn something useful or simulate some aspects of quantum gravity. And the last thing I would like to mention is that although I've been drawing analogies here every now and then with ADS CFT, these properties are really, these are just really a gravitational way of understanding quantum error correction codes. So can we extract the lessons that we learned here in quantum error correction and apply to something more general that's behind this? So that concludes my talk. Thank you very much.
Any questions for Charlie?
So for the non-isometric property, is that a non-perturbative phenomenon or perturbative phenomenon? Here you phrase it like a perturbative phenomenon, but I always think that's a non-perturbative.
Right, it doesn't have to be perturbative. So here I'm assuming epsilon to be small, but in the quantum error correction code, of course, epsilon can be any number.
No, I mean in gravity, it's a e to the 1 of G Newton phenomenon or G Newton phenomenon. E to the minus 1 of G.
That I think, so we haven't thought about that kind of division because that is a more of a artificial division in how we do gravity, right? So in quantum error correction code, it's not clear how you make this identification. Yeah, at least not.
This might be asking the same question, but yeah. So is there like some particular like sweet spot regime of epsilon here where you know, like these pathological effects probably all occur with like some 1 over epsilon. Like you probably need 1 over epsilon applications of a unitary map or something if it's epsilon far from unitary to notice it or something like this. So yeah, is there some like nice regime where all the pieces fit together, or is that not clear?
It's not clear yet. We haven't had the time to look into it yet, but yeah, that's definitely like it.
Why would you be happy with a little bit of non-linear, like a little bit
Yeah,
of
yeah,
pathology?
it's presumably quite pathological. Well,
I guess
if you had an epsilon probability of sending a superluminal signal, would that be very problematic?
yeah, so.
Okay.
Or, I mean, if the problem you're trying to solve is information loss, then why not just have information loss and why have all these things which appear to be much worse in life?
I see.
Even if they occur with some small probability, they're just.
Maybe a very basic question. So I don't quite understand why you are unhappy with the area operator being the identity or proportional to the identity for a single tensor. I mean, for like a big tensor network, which is supposed to represent some, I don't know, ADS time size or something, I would think of the area operator, you know, this like Don Merrill sent some sort of operator, you know, that acts along some sort of HRT cut through your network, maybe even somehow transforms its geometry, but not something that you should be able to, you know, extract anything non-trivial from for a single tensor.
So I think, so for example, if you look at the theorem or something like that, right, it doesn't really specify your code has to be above a certain complexity. So for all these codes, you can define something like that. But the question is whether that area, the calling area actually has matching onto what we geometrically expect to be area. So you're absolutely right that, right, if I go into this more complicated tensor network model that we've shown later on, then this area makes sense. But for the other ones, of course, I'm just using area as like a substitute for the second term in the entropy contribution.
Okay.
But in my code, the area was non-trivial even in an exact setting, right?
Sorry?
In my code, the area was non-trivial as an operator, even in an exact setting without introducing any noise.
Yeah, that's right. Yeah, but well, we don't have an exact stabilizer code construction for that. So it would be nice to construct something that looks like it as well. It's simply not clear to me how to do that with stabilizer codes.
Well, yeah, it's hard to have it's hard to have operator algebras with non-trivial centers coming from stabilizer codes. I mean,
Exactly.
I think there was one paper by some people from Santa Barbara where they did that. I don't know if any of the authors are here and can comment.
It's one thing to have a non-trivial center, right? But here you also have a non-trivial center, and yet you still have something that's proportional to identity. And I completely agree with you that with stabilizer code, it seems hard to do it, which is why here we took the approximate element, which seems like the easiest way to do it.
But I think you're using the word noise to do a lot of heavy lifting for you here, because you know you talked about a whole bunch of things that you were like gravity, but I mean noise is usually something that we don't control very well, right? It's just saying that we have this structure and then the structure is not exactly true. It's only approximately true. But if that's all you say, then pretty much anything can happen with, you know, with the violations. It's like,
right, yeah. So yeah, let me
gravity. These things you were talking about have a lot of structure to them, right?
Yeah, absolutely.
Yeah,
I think noise may not be the right term here. So let me be more precise. I mean the particular kind of coherent deviation from the reference code in this particular sense, at least.
So you really mean skewing?
Yeah, I call it skewing in the
I have a question. So in original happy code, like the term for the area and the bulk entanglement have a sort of in fact counting for the G Newton, right? Because counting like this term, area term, like larger than that term. But here it seems like you introduce an extra parameter of epsilon that's also count for G Newton. So it sounds like you have two parameters corresponding to one. Is there any comment for that?
That's a great question. So it seems like there are two different parameters, but actually they're locked as if you impose this constraint Igarath and Domarov and Shidong. So basically, if you insist that the Rayleigh spectrum be flat, then it forces then the two things actually match.
Any further questions from anyone online? All right, if not, let's thank Charles.